Now we will be basically looking at the partition function of a monoatomic gas. So, what will be the partition function? Of a monoatomic gas. So, as I have shown you that partition function can be correlated to various thermodynamic quantities. Now, we are taking a special case where we are trying to find out the partition function of a monoatomic gas, and from there on we will see how this partition function of a monoatomic gas correlates to various thermodynamic quantities. Okay, so when it comes to a monoatomic gas, so you know this monoatomic system has only the translational motion. It has only the translation. It has only the translation. It does not have. If the system was a molecular system, then it will also have a rotational motion and it would also have a vibrational motion. The molecule will stretch and compress. So, therefore, you also have a vibrational motion of the molecule, and therefore, your total energy would turn out to be E translational plus E rotational plus E vibrational. Correspondingly, your total partition function would look like as Q translational product Q rotational product Q vibrational. But in this case, we are talking about a much simpler system where we have no vibration, we have no rotation as well, and therefore, the energy contribution will have only the translational motion, and therefore, our Q partition function also have only the Q translational. So, let us find out for this simple case what is our Q, and not this. Our system is this. We assume that our gas is contained in a cubic box of length A. So, this is a cubic box of length A, and our monoatomic gas is basically kept in here. Now, if you recall your first year chemistry, you know that for a particle in a box system, the energy was n square h square by 8 m square, where n is a quantum number. It is a quantum number and it is an integer. So, this is the energy for a particle in a box. But if you remember, this expression was for the movement of the particle in one dimension. Now, if we make use of that formula, here our Q translational will be sum over n e to the power minus beta n square. I would write h square first and then n square by 8 m square, but this is in one dimension. Our gas is contained in a cubic box, and therefore the gas particle can move in all x, y, z direction. So, in that case our Q translational in 3D would be, okay, here n is equal to integer 1 to infinity. We can, so in 3D we can write nx, the movement of the particles in x direction, e to the power minus beta nx square h square by 8m square plus ny 1 to infinity e to the power minus beta ny square h square by 8m square plus we have the z component nz is equal to 1 to infinity e to the power minus beta nz square h square by 8m square. All right. So, this is Q translational in 3D. Now, if you see is the gas is in a cubic box and particle can go in x, y, z direction equally. It can go to any direction with equal probability. So, therefore, we can write Q3D. Okay, let me leave some space in the left hand side. So, we can write Q3D translational is equal to n is equal to 1 to infinity e to the power minus beta n square h square divided by 8m square to the power 3, because our x, y, z all three directions are equally probable and they are the same. So, we can simplify this further. Let us see how we can simplify. We basically now apply few mathematical tricks. So, here our sum goes from n is equal to 1, because the quantum number is an integer, and for the sake of mathematical simplicity we want to change this limit from n is equal to 0 till infinity. How do we do that? So, we write as it is and then we simply put minus 1. Since e to the power 0 is 1, so just by when I put n to the power 0, so I get e to the power 0 which is 1, and that one I am basically subtracting out here. Now, since this number is much larger than 1, we can write this as n is equal to, these are mathematical tricks to make our calculation tractable. So, since m square to the power 3, since this quantity is much larger than 1, and therefore we can neglect 1. The second trick is, since energy gap is very small, in every system, in this case in the quantum system, since there are many energy levels and the energy gaps are very small, so we can assume we can replace this sum by integral. So this we can write as 0 to infinity e to the power minus beta n square h square by 8 m square dn. To the power cube to the power 3, and we return with the logic that since energy gaps are very small, they're very small, so you can assume that it's like a continuous energy states, and therefore we change the sum to integral. Now how do we simplify this integral? Let us say that b is equal to beta h square by 8 m square, or let's take b is equal to beta h square by 8 m square. So therefore, from here I'm writing here. So therefore, I can write this expression as Q3 translation is equal to sorry, this sum basically goes here, not inside. So this Q3 we can write as 0 to infinity. I'm just replacing beta h square 8 m square with b, and therefore this would look simpler now, dn e to the power minus beta n square to the power 3. So the right. So from here basically we are writing this. Okay, now let's see how we can simplify it further. So we have beta b is equal to beta h squared 8 m square. And we now trying to find out what is e to the power minus beta n square dn. So what is e to the power minus beta n square dn with the limit 0 to infinity. Let us say n square is equal to x. So therefore 2n dn is equal to dx. So from here you get dn is equal to 1 by 2n dx, and since n square is equal to x, so here I replace n with x, and therefore I get half of x to the power minus half, dx is as so half of x to the power minus half dx is my dn. Therefore (0 to infinity e to the power minus beta n square dn now becomes 0 to infinity e to the power minus beta x, half comes here, x to the power minus half dx. So, half 0 to infinity e to the power minus beta x, because n square is equal to x, and dn we got here, that half of x to the power minus half dx, and that is what we have put back here. So, we get half 0 to infinity e to the power minus beta x, x to the power minus half, yes, x to the power minus half dx. And this is standard integral. Oops. This is a standard integral, and the value of this standard integral is half of square root of pi by b from standard integral. So, if we put it back here, if we put it back here, and this will go to the next page. So, we are basically got dn here, we got e to the power minus bn square dn is equal to half of pi square root of pi by b, and therefore, we can write q, I am not writing, it's implied that it's a 3D, 3-dimensional, is half of square root of pi by b to the power 3. If you recall, we taken b as beta h square by 8m a square, which we are putting back. Since b is in the denominator, so it becomes, so b was basically beta h square and 8 divided by 8m a square. We have put back the beta and to the power 3. So, this is our q. If we simplify, this will turn out to be 2 pi m kt, where k is the Boltzmann constant, divided by h square 3 by 2 and volume, because you have a square root of a square, which is a, and a to the power 3 is nothing but the volume of the box, and that is v. So, you got q of a monoatomic gas as v divided by lambda cube, where lambda cube is h square divided by 2 pi mkt to the power 3 by 2. And this lambda, having a dimension of length, is called the thermal de Broglie wavelength. thermal de Broglie wavelength. Okay, so this is the expression what we were looking for, and we got it finally for a monoatomic gas, the expression for partition function. So expression of partition function for a monoatomic gas is nothing but volume divided by the cube of thermal de Broglie wavelength. So now, since we have the partition function of this monoatomic gas, let's find out different thermodynamic quantities. So the first thermodynamic quantity we can look for is the energy. So what is the energy of a monoatomic gas system? So as you know, as we have seen already, E is total energy Ni epsilon I. So epsilon I and Ni I will write again in terms of Boltzmann distribution law, which is N by Q e to the power minus. So now I am writing in terms of beta epsilon I for a reason. I am not, instead of 1 by kT, I am writing it is as B. So we got N by Q sum over I epsilon I e to the power minus beta epsilon I. And again we had Q is equal to sum over e to the power minus beta epsilon I. So if I want to find out dq by d beta, what we will get from here is minus, because since we are differentiating with respect to beta, so the minus comes out from here, and beta del dB by dB is 1. So essentially what we are getting is minus e to the power minus beta epsilon I. One epsilon I would also come. So minus so it would be minus epsilon I. So beta is 1, but you have epsilon I e to the power minus beta epsilon I. That's your dq d beta. So if we put this back, minus epsilon I e beta epsilon I in this expression, from here we get E is equal to we get E is equal to Ni epsilon I and Q. So we get E is equal to minus yes, we get E is equal to minus N by Q dq by d beta, which also can be written as minus N d ln Q by d beta. That's the energy for this monoatomic gas. Now we got Q from the previous expression, and we are putting back that Q expression in here. So we can write that as is equal to minus N del beta, and ln, this was our Q, which was 2 pi m by beta h square 3 by 2 v, and we are doing that at constant volume. So that means at constant volume. So if you simplify that, this should be minus 3 by 2. You can do this yourself. This should be n del delta b ln 1 by b. So let's make sure that everything is correct. So ni epsilon I epsilon n by q to the power minus beta epsilon I n by q. We have put back this one in here, and therefore you got it to the minus n q dq d beta, which is nothing but minus n del dl n q d beta, and we are putting back the expression of q for the monoatomic gas, and from there you got we want to keep the volume constant, and therefore you got minus n del dB ln 2 pi m beta h square 3 by 2 volume, and that gives you minus 3 by 2 n del b ln 1 by b. On simplification, you get E is equal to minus 3 by 2 n minus minus 3 by 2 n del b, sorry, what we had in the last one, we had del b ln 1 by b, and therefore it should become 3 by 2 dot n beta minus 1 by beta square, which is nothing but 3 by 2 n. So we have minus minus plus and 1 by beta, which is nothing but 3 by 2 n kt. And as you know, this is the energy of a monoatomic gas system. So we started from the definition of partition function, and then we using that partition function definition, we have come up with the thermodynamic expression, what you know of the total energy of a monoatomic gas system as 3 by 2 n kVt. What is the pressure? Of this system. So pressure, as you know from your thermodynamic law, and which we already have used to get the relation with the partition function, we got P is equal to nkt del ln q by del V at constant temperature. We got it few slides back. So now if we put back Q from the monoatomic gas, we simply get nkt del V ln 2 pi mkt by j square 3 by 2, and we had a volume term. Since everything is constant here, so we get simply nkt del V ln V, because everything is constant here. So that gives you nkt by V, and thus your PV is equal to kVt, which is the equation of state. Equation of state of an ideal monoatomic gas system. So what I want to point out here is that thermodynamics and statistical thermodynamics they are they complement each other, and thermodynamics, statistical thermodynamics, basically giving you the microscopic information in terms of partition function here, and that partition function can bring out not only the thermodynamic expressions, but also can correlate to many classical equations or expressions you know of, like P is equal to nkBT, or total energy is equal to 3 by 2 nkBT, where kb is the Boltzmann constant, which I have written as k here.